Hey everyone, so we need to talk about one of AI's biggest, and I mean biggest, problems. As AI gets more and more powerful, it's also getting hotter. In fact, it's getting so hot that the future of computing, well, it might not be on planet Earth at all.
Here's the core issue, and it's pretty simple but also kind of alarming. The incredible exponential growth of AI has created this just ravenous appetite for electricity. And running these gigantic models generates so much heat that cooling our data centers here on Earth is quickly becoming a massive, unsustainable problem.
To put a number on that, just look at the US. Back in 2022, data centers were pulling about 17 gigawatts of power. By 2027, that number is projected to pretty much double to 35 gigawatts. And guess what's driving that surge? Yep, it's AI. We're literally running out of power, running out of water for cooling. We're running out of planet.
So the next logical question is, why not just move it all to space? I mean, you've got unlimited solar energy, the infinite cold of the void. Seems like a perfect match, right? Well, for decades, space engineering has been stuck in this trap, a very specific temperature trap, that made this whole idea basically a non-starter.
You see, for as long as we've been sending things, and especially people, into orbit, the main idea has always been to build this cozy little bubble of Earth out there in the vacuum. Just think about the International Space Station. Everything, from the astronauts to all the sensitive gear, had to be kept at a comfortable room temperature.
This old-school human-rated way of doing things locked the operating temperature at around 20 degrees Celsius, or 68 Fahrenheit, and that made sense. You had to keep the astronauts and the early delicate electronics safe. But to maintain that temperature, you needed these enormous, complicated systems with motors, pumps, even toxic fluids like ammonia. The result? It was just horribly inefficient for something as power-hungry as a modern data center. And here is the absolute crux of the problem. In the vacuum of space, the only way to get rid of heat is to radiate it away. The efficiency of that process all comes down to the temperature difference between your hardware and, well, the rest of the universe. Trying to radiate a lot of heat from a surface that's only 20 degrees Celsius is like trying to empty a swimming pool through a coffee stirrer. To get rid of serious heat, you needed a comically large, heavy, and expensive radiator.
But that entire way of thinking is now being completely flipped on its head. There is a revolutionary new way of looking at this, a new paradigm that just totally changes the economics and the engineering of computing in space.
This is the question that changes everything. What if we just threw out that old rule about recreating Earth-like conditions? What if we just designed our space systems around what the hardware actually wants, instead of what a human astronaut needs?
And here is the big aha moment. A modern AI chip, something like an NVIDIA H100, isn't some delicate flower. It's a piece of silicon that is literally designed to run safely at temperatures around 85 degrees Celsius. It likes to be hot. So by trying to keep it at a chilly 20 degrees, we weren't protecting it, we were just making it incredibly difficult to cool. Now, this isn't just some clever engineering trick, it's backed by some really fundamental physics. It's called the Stefan-Boltzmann Law, and it basically says that the amount of power you can radiate away from something is proportional not just to its temperature, but to its temperature raised to the fourth power. That little t to the fourth, that's the secret sauce. It's a superpower. It means even a small change in temperature has this colossal impact on how fast you can shed heat. Let's make that real. What does that fourth power thing actually mean? Well, check this out. If you increase a radiator's temperature by just 20%, say from a room temp 300 Kelvin up to a hot chip 360 Kelvin, you don't get a measly 20% cooling boost. Nope. Because of that fourth power magic, you get a 100% boost. You double the amount of heat you can radiate away from the exact same surface. And the result of that is an absolute game changer. If you can radiate twice as much heat from the same area, it means you only need a radiator that's half the size and half the mass to cool the exact same GPU. This just completely rewrites the rules for building data centers in space. Okay, so let's make this really concrete. Let's do a side-by-side comparison. We'll put the old human-rated philosophy of the International Space Station up against this new AI-rated philosophy from a company like StarCloud. The difference is just stark. The legacy approach runs cool, so it needs those massive rotating radiator wings and wastes a ton of power on pumps and heaters just to keep things stable. The new AI-rated approach, it lets the silicon run hot, up at nearly 90 degrees Celsius.
That immediately slashes the radiator mass in half, and the power needed for cooling, it drops to pretty much zero because it's all done passively. Okay, but there's an obvious catch here, right? I can hear you asking, if your radiator is already super hot, what happens when it gets blasted by direct sunlight? Wouldn't it stop being a radiator and just become a solar oven absorbing heat and frying your chips? That's exactly why the ISS radiators have to constantly rotate to stay in the shade.
Well, the solution here isn't a complex machine, it's just really, really clever orbital mechanics. The trick is to put the satellite in what's called a Dawn-Dusk orbit. It means it flies perpetually along the terminator, that line between day and night on Earth. It's basically surfing the edge of sunrise and sunset forever. The benefits you get from this one simple orbital choice are just immense. Think about it. One side of the satellite, the side with the solar panels, gets 24/7 sunlight, non-stop power. The other side, with our hot radiators, is permanently pointed away from the sun, facing the cold, dark void of deep space. They never get hit by sunlight, so no heavy motors needed, no complex moving parts, and you get a perfectly stable thermal environment to dump all that heat into. And this is what the whole thing looks like when you put it together. It's not one single giant space station. It's these modular, almost container-like data centers that can be launched and then docked together to scale up. It's a system that's designed from the ground up to be efficient, to be scalable, and to work with the laws of physics instead of constantly fighting them.
So let's bring it all home. What does this new approach really mean for the future of computing and for the future of AI itself?
When you put it side by side with a traditional data center here on the ground, the advantages are just incredible. On Earth, cooling can eat up to 40% of a data center's total energy budget. 40%! In space, using this passive design, that number is effectively zero. On Earth, you might get 4 to 6 good hours of peak sun a day for solar. In a sun-synchronous orbit, you get it 24/7. It is just a fundamentally more efficient way to do things.
And look, this is not just some theory on a PowerPoint slide. This is actually happening. In late 2023, the StarCloud 1 mission successfully launched and operated a commercial, off-the-shelf NVIDIA H100 GPU in orbit. They ran language models on it, they trained a neural network, they proved that this entire concept works in the real world.
This whole shift is being noticed by the big players in the industry. As Christophe Valorge, who is the CTO at Thales Alenia Space, puts it, moving these super energy-intensive workloads off our planet isn't just about getting better performance. It's about finding a more sustainable and, frankly, eco-friendly way forward for the entire AI industry.
And that leaves us with one last, kind of mind-blowing question. As AI models just keep getting bigger and bigger, scaling way beyond the power and cooling capacity of our own planet, it seems more and more likely that the hardware needed to give birth to a true artificial general intelligence, well, it might not be built on Earth at all. It might be born up there, in the cold, efficient, sun-drenched vacuum of space.